earlier we defined these operators T delta tilde to be given by T star U delta T. We said that if delta is at most square root of P minus 1 over Q minus 1, then if Q is at most the norm of F, but now there was something a bit arbitrary about the coupling, because we basically made an arbitrary choice of basis when we applied Ramsch between the columns. And there's a simple way to fix it just by first choosing randomly a basis. And the way to fix the operator is to define this operator T delta is the expectation over B from SUN, and then the T RB U delta and RB T U delta T star and then RB star. So RB is this multiplication by right operator that we had earlier. If you just average, then we still preserve the same hypercontraction properties. But now you can show that it's an exercise that T delta commutes both with the right action and the left action. And the left action. And now you give a sketch of okay. So we know that this operator is hypercontractive. This is we established. This we do have. And now the question is, what can we say about the eigenvalues? Okay, and okay, now we have the following intuition that's going to help us. So I'm not going to use the proof because it's complicated, but I'm going to give some intuitions why this is true, that the eigenvalues behave like the eigenvalues of the noise operator. Okay, so so let's say I take a matrix in S1 So first, the intuition is that if I look at the every b times b minor of A is roughly Gaussian. Okay, so we know that the first column of matrix in SU1, it's a vector in the sphere, and the coordinates of the sphere behave roughly independently. And similar thing is true for a matrix in SU1. Okay, so that's the first thing, and then another thing is that, well, here you have this random walk that corresponds to multiplying by a random matrix, then taking a random matrix whose Gram-Schmidt is the matrix that you started with, then you apply noise in Gaussian space, then you apply Gram-Schmidt again, and then you multiply it by the conjugate of this matrix. But eventually all of this behaves like independent noise. It's reasonable that if you do something very complicated, it's eventually going to behave like random noise, independent random noise also. And it turns out that the representation theory helps us with the first part of the intuition. So, it turns out that if you take a matrix in SU1, if you take an eigenspace, you can always find in this eigenspace a special function that only depends on the d times d minor. So, in the Boolean cube, we also have these spaces v equal to d of homogeneous polynomials of degree d. And inside every space v equal to d, we could find a special function, the character, that depends only on d coordinates. Which we call the d junta. So it's a function that depends only on d coordinates. Okay. And it turns out that the same thing is also true in SU1, that you can find in every space v equal to d. You can find a junta. Okay, that's obvious, but you can actually find an analog of this fact, and you can you can even find something stronger than a d junta. So that leads us to the notion of a comfortable d junta. Let's take x1. So let's say that d is smaller than n over 2, and a function on SU1 is a comfortable d junta. if it's of the form, so you sum over permutations in SD, and you have A sigma, and then you take the product of let's call it. So f of b is the sum of A sigma times the product of EI sigma I. So it's not only a function that depends on the becomes D minor, but it's a multilinear function. And it turns out that every eigenspace of a nice operator that commutes with the action of the group from both sides, it contains such a function that's easy to work with. Okay, maybe I should give an example though. So I don't know, you can take the function and it sends A to A11, A22, I guess real A11. Yeah. Okay. I don't know. So this function is comfortable to point out. But then you can also minus the real part of A12, real part of H1. If you want, you can work instead with FON, and then you don't have to take real parts. Okay. Anyways, you have these nice functions, and then the fact is that from representation theory. So suppose that T is a self-adjoint operator on L2 SUN, and then T RG is equal to RG T, and also T LG equal to LGT for all G in SUN.
Did you define energy?
Yes, so
shift. Yeah, but I thought you only used R.
I only used R, but it said somewhere.
Okay.
Okay. Okay, so we have a self-adjoint operator commutes with action from both sides. Then then the spaces B equal to D are T invariant. And each eigenspace of T inside V equal to D contains a comfortable difference. Yeah, so basically, if you wanted to compute the eigenvalues of the noise operator in a very complicated way, then you can say that it commutes with the action of the symmetric group and with translations. So you know that eigenspaces are homogeneous polynomials, and then you can say that you can choose your favorite homogeneous polynomial to compute the eigenvalues. So you can choose the character, and then to plug in the value of the character, to plug in the character and check what happens. And here you can do a similar thing. So, yes, so to lower bound eigenvalues, you okay. To lower bound eigenvalues, you lower bound T delta F L2 norm for every comfortable different F. Okay. And then this intuition that small d times d minor behaves like a Gaussian d times d minor. This is more and more correct when d is smaller, so somehow. Yeah.
So the justification of the fact is that, correct me if I'm wrong, but like the reason that the fact is true is that every subspace in the decomposition of L2 SUN via like left and right actions contains a comfortable D-junta, right? Like you can say
every sub G times G representation contains a comfortable D-junta, and then yeah. And somehow there is a duality between the representation of SUN and of the symmetry group, and that's why you can find these functions that are related to the symmetry group inside every space. Yeah, but the point is that in every space V equal to D, you can find, let's say, a function, a nice function, depends on the D times D minor, and then this intuition that on D times D minor, on a D, yeah, so if you look at the small D times D minor, everything behaves sort of independently, and then you can try to make calculations, but it's more complicated than that to actually compute the eigenvalues, but at least you have some intuition for why such things should work in principle. Okay. So are there any questions before we move to a different topic? Okay, so here everything was about compact groups, but what can we say about finite groups? Yeah, so can we get something similar for finite groups? Can we get better mixing results? For finite. again, it turns out that the answer is, in a sense, no. So up to some polynomial factors, there is the following fact. It shows that you can get more than polynomial improvements. And this fact uses the representation, the classification of finite simple group. Okay, so that's by Nikolov and Peter. So it says that if a representation from G to exists with rho-not identity. So if there exists a representation of dimension D, then there also exists a subgroup of index poly D. Because this is a subgroup of G with the density of H. So the index of H in G, polynomiality. Okay. So that means that you don't have mixing, because if you take two random elements inside a subgroup, the product is going to be there always. So it means that an analog result can't hold for the finite groups, or every finite group, basically. You can't do anything. So that's for every finite.
So this means that you cannot go beyond the quasi-randomness.
Yeah. So basically, yeah, what Gauss proved tells you the answer. But it turns out that subgroups are the only obstruction somehow. And it turns out that what you can show is that if your function is not correlated with any subgroup, then you do have hypercontractivity, and that's related to hypercontractivity for global functions. Okay, so we define simple groups. Okay, you can prove hypercontractivity for global functions. And then prove the following result. So
maybe you want to define global functions?
So I'm going to talk about it soon, but I just want to give the following corollary of hypercontractivity for global functions. Or more precisely of this combination with hypercontractivity for global functions with the representation theory of the group. And
Basically global function.
yeah, so it's undefined, but basically here it means that F doesn't, its L2 mass is not concentrated in any subgroup, because that's an obvious obstruction to mixing. So somehow you have to exclude it, and once you exclude it, you have hypercontractivity. Okay, so that's this. And so there, even though you don't have mixing, you can prove the following result, that so you can show that if A is a subset of G and G is a finite simple group, and G is not equal to AN, so it's a finite simple group that's not the alternating group, then you can show that AA inverse okay, so earlier for large sets we could deduce that this is everything. Here it's not everything, but you can say that this set contains a large subgroup. It contains a subgroup H of density and its polynomial density of N. And perhaps surprisingly, such a result is still open if you look at subsets of Zemo 2 to the N. So in Zemo 2 to the N, which is a much simpler group, this is still a very central open problem in additive combinatorics. But somehow you can do it in the non-abelian setting.
So what goes wrong in AN?
So it's related to the representation theory, but in AN you can get something similar but with log n here. And instead of taking 4 products, you have to take log n products. You can say something, but it's still open to get it to be polynomial in this form.
It should be true.
It should be true, yeah. The conjecture that it's true. So somehow in the abelian setting, such result is known as a Bogolyubov result or a Bogolyubov-Ruja result, and it's related to Gauer's norm to establish such things even like in Zemo TP to the N. So let's talk a little bit about degree decompositions in finite groups. And then we can see how Bonami's lemma goes wrong, even for the symmetric group. And then we'll explain how to fix this issue. So let's start with the symmetric group. So in L2 of the symmetric group, you can define dictators by letting xij of sigma to be the indicator that sigma of I is equal to J. And every function can be written as a polynomial in the dictators. So we can define the degree to be as a polynomial in the dictators. And here we see already that these dictators are cosets. They're all cosets. And if we take this definition, we can see immediately that Bonami's lemma fails. Because if we take the indicator that sigma of 1 is equal to 1, then L2 norm is going to be 1 over root n. But the L4 norm is going to be n to the minus 1 over 4, which is much larger. So we see that there is a huge gap between the L2 norm and the L4 norm, even for degree 1 functions. So somehow dictators have to be excluded from hyperconvertibility. Okay. Okay. Another example that you can take is GLN FP. So functions on open matrices over FP. There you can also define dictators. And you can define the dictator corresponding to V for every V in FP to the N and U in FP to the N. You can define a dictator XVU to be the indicator that AV is equal to U. And then again, the degree of a polynomial is the degree of a polynomial in the dictator. It turns out that people working in representation theory, they came up with this notion independently when they wanted to. So in GLNFP, you have a complete classification of the irreducible representations, but they realized that this notion of degree, you can associate it to a representation, and it captures most of its properties, or at least many of them. And for GLNFP, the representation theory was known for a while, but actually, for the other finite simple groups, it's much more involved. So you can, so you can generalize to other finite simple groups, to all of them. And then this thing is only a recent work of representation theories. basically classifying the dimensions of representations of level D. Which is the analog of the second theorem 2 that we had earlier about the lower bounds and the dimensions. This was done only recently. Of Larsen, Keevash, and Goran. And the motivation was to obtain character bounds. So the motivation was to upper bound the values of the traces of the representations. And in order to do that, they used Tal cohomology and the Lin-Lustig theory. And it turns out that you can use hypercontractivity to get everything without the Tal cohomology and the Lin-Lustig theory. So somehow hypercontractivity removes the difficult algebra. That is that. So you can use hypercontractivity instead. But it's important that it's hypercontractivity for global functions. So let me tell you what's it about. So the simplest way to discuss hypercontractivity for global functions is the p-biased hypercube. Because earlier we said that the problem was that there is a gap between the 4 norm and the L2 norm of the dictators. And this happens in the Boolean cube when p is small. Okay, so if you consider 0, 1, n with the p-biased distribution, where the probability of getting one is p in each coordinate independently, you have then we have the same problem. The function xi as a 2 norm root p and the 4 norm p to 1 over 4, so there is a huge gap between the 2 norm and the 4 norm, and therefore you don't have one lemma. Okay, so Bonami fails if Q is small. Or even a Hinching's inequality fails. Other question?
Can you remind us what is global functions?
No, I didn't define global functions.
This is an explanation why Bonami will not work for general functions, and then we'll have to define global functions, and then it will work there.
Okay. Okay, so I'll define what the global function is. So let's say that f let's say that f is R global. Okay, so it's clear that something goes wrong in the p-bias cube because of this, and we have to fix it somehow. And the way to fix it, one way to fix it is the following. We can say that f is R global if the expectation of f squared of x given that xs is y is at most R to the size of s times the L norm of f squared. Okay, so this is for every set S. Every y in the 1 to s. Okay, so we can take the L2 norm of f conditioned on x being in some smaller hypercube. And we want the L2 norm of that not to jump by a significant factor. So if you look at the Boolean cube, we know that if we condition on an event that happens with probability 2 to the minus s, the L2 norm can jump by at most a factor of 2 to the s. But in the p-bias cube, it's no longer true, so we have to assume that. Okay. Yeah, so this excludes the dictators. In the dictators, if we so in the dictator you can restrict one coordinate and make the L2 norm jump from root p to 1. So it jumps by a significant factor for the dictator. And somehow this notion excludes the dictators from the. Right, so we take that, for example, xi, and the L2 norm of xi is root p. But if we take the expectation of xi, given that xi is 1, then this is 1. So you get a significant jump. So you have to take R to be at least p to the minus 1/2. Okay. And what we proved is that once you assume this globalness, then you can, once your function behaves like a function in the cube, then you get hypercontractivity. Yeah. That there exists absolute constant. Such that if delta is at most C over R, probably root R. And F is our global. And then tilde delta F and all the most delta. So I gave the version of hypercontractivity for 4 and 2. There is a version with Q and 2. I don't think we have a version for every two norms, but I guess you can deduce something using interpolation. But anyways, once you assume that your function is global, then you have hypercontractivity. Are there any questions about the state?
Does this semi-group preserve our globality if you use this monami vector semi-group on our global function? We will get our global function.
Probably not, I want to say.
Probably not.
Probably not, yeah. Yeah, I mean, okay, but there is a way to define it. No? Yeah, just, okay. There is an equivalent definition that might preserve it.
This is the standard semi-group.
Yeah.
So it's not the biased version.
The p-biased version. Yeah, sorry, I should define t delta. So, thank you. So on okay, so we need to define the noise operator on the p-biased cube, and this p-biased and the noise operator. If you start with a vector that's p-biased, it should be also p-biased. So n delta of x and is chosen by probability that yi is equal to xi. So with probability delta, you remember it. So it's going to be delta. But then if you forget it, you also have a chance of hitting xi by chance. So it's going to be this.
I think you need the other way around. It's 1 minus delta plus.
With probability delta, you remember it, and if you forget it, you have you re-randomize it, and with probability mu p of xi, you get xi.
So the probability of re-randomizing is 1 minus delta?
Yeah. Delta is a correlation.
So when delta is 0...
It's independent.
Yes, okay, yeah, that's...
yeah, use delta.
Yeah,
and
fine, yeah.
Delta is the usual rho, but rho and p, it's confusing when I write them on the boards. Switch to delta. Okay, so this is y, and then the operator is defined similar. Well, so p delta f of x is the expectation of the y from n delta. And then, and this operator has this similar eigenvalues. So Yuval talked about the Fourier expansion over mu p. I think so. Chi-S was the product over I in S of xi minus p over root p1 minus p. And then T delta over is the right eigenvalues. So it has the same interpretation as somehow analytically truncating the function, or probabilistically truncating it. Yeah, then you can deduce Monamit's lemma for global functions. Okay. So are there questions about it? Okay, so basically you have a replacement for hypercontractivity once you assume that your function is global. And then this is the right notion when you try to generalize over groups, because they also have functions, they also have dictators that have small expectations, so they behave like the p-bias distribution.
But all this coming cube with mu p, we still have the same Laplacian, for example, right? Laplacian cannot change, right?
Yeah.
So these are not eigenfunctions of Laplacian.
Did you check it?
No.
Yeah. So the function you take a function and you subtract when you randomize the coordinates.
The derivatives don't change, but the Laplacians do change. So.
Okay.
So the i's partial derivative at x is f of x minus the average of f with respect to the i's coordinate with respect to mu p. So this is the i's partial derivative.
So you don't average over the neighborhood with a uniform distribution, you average over the neighborhood with a distribution that's
the
constant.
Laplacian is different. Okay.
It's like global dynamics. That you forget one coordinate and resample it for the back distribution. I don't know. Maybe it's funny to say that the p-bias distribution is like global dynamics. Okay, so what more? So you can prove the hypercontractivity. Okay.
But in the usual case, we have this p minus 1 square root coordinates 1. So very sharp. And here it's...
Yeah, so here it's 4 and 2, so everything is a constant, but yeah, so it's sharp up to a constant because the noise is just a constant, and I don't remember whether we have the sharp hypercontracted result or not. Probably not. Probably we have it up to a polynomial. It's interesting to think about getting the right bounds there. Okay, so how do you prove this? The idea is to use induction at some point, but before that, here is a more analytic version of the statement. So the Laplacians change, but the derivatives, you can define them in a similar way. The discrete derivatives, you can plug in one in the ice coordinate, and then take the difference when you plug in 0 in the ice coordinate. Okay, so this definition doesn't change. Here I guess it's, you don't, yeah. Here you can keep it like this. The 2 is somehow related to the uniform measure. And it turns out that DAF is the sum of f and s chi s minus I. And then you have to divide this by root p plus 1 minus p. Okay. But the notion of globalness checks what happens when you restrict several coordinates, not just a single coordinates. And therefore it makes sense to define these iterated derivatives. So dij of f, you can define it as this di dj of f. And similarly, you can define dsf for all s. Okay. And now the result is that another version of hypercontractility for global functions global functions, and this is now a statement for all functions, a more analytic statement that takes the form yes, suppose that void mod C delta then P delta of F for known to the form is at most the sum over S of P to the power S over P. DSF L2 norm to the 4. Somehow we switch between L4 and L2, but you don't get the L2 norm of the function, but you get the sum over all the derivatives. And the globalness implies that the L2 norm of the derivatives are small. And you can use
Not too large.
Yeah, not too large, and then you can get just the L2 norm of F. Somehow, if your function is global, you can apply extra noise and get rid of all the sum over S, just get L2 norm of F. Okay, so how do you prove that result? So you can try to prove it by induction on N, and you'll fail somehow. Somehow hypercontractivity relies on the fact that you can interchange 4 norms and 2 norms in one direction. So you have this inequality that if you take
Switch to
somehow in the proof of hypercontractivity, you use the fact that if you take f of xy, and then you can take L2 with respect to x and L4 with respect to y. Then this is at most what happens when you first take L4 norm with respect to y and then L2 norm with respect to x. If x and y are independent. And this is what makes the induction work, because you replace the 4 norm by L2 norm, you change the order, and then replace back the L4 norm by L2 norm.
by the inductive hypothesis.
Yeah. But here there is a combination of L4 norms and L2 norms, and then you would have to, at some point to change the order of the L2 norm and the L4 norm in the wrong direction, and you won't be able to make this work. So instead, the idea is borrowed from work of Elchanan and Ryan and Hausdorff about the invariance principle. Did I spell it correct? Okay. Okay. So, and the idea there is to basically, so there what they did is to take the Fourier coefficients of a function on the Boolean cube and take a similar function in Gaussian space with the same Fourier coefficients. They said that their distribution is somehow similar. And here we'll do the same thing. We can take, but we can even switch to the uniform cube. So we can define f tilde to be the sum over f at s and then and you take chi s 1/2. So maybe I should write just the product over I and s and x half. Yeah, so this is a function on -1, 1. Now the idea is that in the uniform cube, we can change the two norms and four norms freely up to applying some constant noise. So here is another variant of this theorem that now only involves L4 norms. So the statement with the same hypothesis is that this is at most e to the minus p to the s over 2. And here you have ds of f tilde, 4 norm to the 4. And the idea is that you can always introduce an additional constant noise to move the noise back here, and then use hypercontractivity to replace the 4 norm with an L2 norm and get this statement.
So we have L4 norm to the right, the uniform.
Yeah. This is L4 in U1. Okay, and it turns out that the proof of the theorem is an easy induction of this one.
So on the left we have mu p.
Yeah, and here it's in mu p. So somehow, yeah, you start with an L4 norm in mu p, and now you replace it by an L4 norm in the uniform measure, but you have to pay with all these derivatives. And you said that basically when the derivatives are small, this invariance principle intuition tells you that the distribution should be the same, and then the L4 norm should be roughly the same as the in mu p should be roughly the same as the L4 norm in the uniform measure. But yeah, but the invariance principle is an intuition. The proof of this statement is by induction.
And ds is still the biased ds on the right hand side.
ds has no mention of p, it's just.
Oh, I see. It has some normalization, right?
No, I didn't normalize it.
Normalize the line.
So you could normalize it, but I didn't normalize it, and then it has this. It's not on the bottom.
Okay, but the way it was defined, it's just the difference between the value of f at x when you put 1 in the ith coordinate and the value of f when you put not 1.
And then you have to normalize when you take the Fourier formula for it. You have to divide by root p over 1 minus k.
So you apply constant noise to, like the hypercontractivity you apply on the unbiased hypercube is just constant? Is this some constant noise? Or?
Yeah.
Okay.
Okay, so this you prove by induction. Yeah, so here you can probably get the right constants, because this you can reduce to n equal to 1. But then in this statement, you have you have some noise that you apply. So let's prove this hypercontractivity for global functions. From the theorem. Yes, what you do is you apply it with T1 over root 3 of f instead of f. And then you get that T delta over root 3 of f transformed to the form is at most the sum over s plus t to the s over 2 and ds of t 1 over root 3 of f form to the form. Both the noise operator and the derivative.
There's a tilde over this. Yeah, okay, there's a tilde actually over both of them eventually, but
Yes.
but the tilde of t 1/3 of f is
Yeah, so you have an operator tilde, you have an operator ds, and you have a noise operator, and they all essentially commute. These two act to a factor of 1 over root 3 to the s. So basically this thing, okay, let's just write what it's equal to. Okay, so this is equal to 1 over root 3 to the s, p to the s over 2, and then we have t 1 over root 3 and ds tilde of f, because all these operators, they have nice Fourier formulas, so it doesn't matter if it's over the Keevash cube or the uniform cube. Yes, so somehow the Keevash noise operator became a uniform noise operator. And this thing here is at most get rid of this 1 over root 3 to the s, which only works in our favor, and get ds.
No, it's not very clear, because really, I mean, to which function you apply the previous inequality?
You apply it to the function t 1 over root 3f,
Right.
and then
Yeah.
this is t delta times t 1 over root 3 of f,
Yes.
and then here you have ds over 2, ds.
Right. So
And then this thing here, I'm claiming that this equals to t 1 over root 3 in the uniform cube of f tilde.
is it clear?
So that follows from the Fourier formulas, because both of them just multiply chi s by 1 to the s.
We just move ideal spaces.
Yeah. Fourier-wise, nothing changes basically. And then you want to, and then this thing here becomes 1 over root 3 to the s times t1 over root 3 of ds of f tilde. So this is just some, if you take T1 ds and you try to commute them, you get a factor of rho to the s, because the derivatives decrease the degree. Okay. Eventually you get this thing, ds of tilde is 2 known to the form And then you get sum over f, es over 2. And the L2 norm, now you again don't care whether it's over the uniform cube or with f on the p bias cube. So this is equal to ds over f. And in a L2 of mu p. And this is what we wanted. And okay, so somehow it was very crucial that we're passing to L2 norm for this approach to work. It would be interesting to understand the LQ to LP variance of this. Okay, I think it's a good time to stop.
So one second. In one place you have mu1 half.
Yeah.
And
So here it's in one
in
half.
this hyperconductivity is just the usual view. And then you suddenly jump back to
Yeah.
Right, so the point is that this encoding,
switching
switching
it's
curve.
L2 doesn't
Yes,
matter.
yeah, and L2, yeah.
Yeah.
If you switch the characters and you
it's
switch
fine.
from
Yeah,
L2
yeah,
of the
yeah.
bias to the, yeah.
Amazing.
And so basically we have, I don't know, maybe it's good to have a recap that the reverse direction. So we have this theorem that we prove. I don't know, we have some theorem that we prove by induction that only involves L4 norms, but on one side it's in mu p and the other side it's mu 1/2. But then in mu 1/2 we can apply extra noise to switch the L4 norm to an L2 norm. And in the L2 norm we can move freely between the p bias cube and the uniform cube because everything there is a spectrum. And everything has Fourier formulas that are compatible. I think this is a good place to stop.